What if the biggest secret in the universe isn't a hidden planet or an alien civilization, but a force quietly orchestrating the end of everything? We're talking about dark energy, an enigma that makes up 70% of our cosmos, yet remains completely unknown. This mysterious phenomenon is pushing our universe toward an inescapable demise, and understanding it is crucial to comprehending our own existence. For decades, astronomers believed the universe's expansion was slowing under the pull of gravity, but in 1998, two teams of scientists, one led by Saul Perlmutter and another led by Schmidt and Adam Riess, discovered that the expansion was actually accelerating. They used type Ia supernovae as cosmic mile markers, comparing their apparent brightness with their known intrinsic brightness to determine distances. The results were undeniable. The galaxies hosting those supernovae were farther away than expected because the universe had been speeding up its expansion for billions of years. That single discovery reshaped cosmology and forced the scientific community to confront the reality of dark energy. Dark energy is the term we use to describe the unknown cause of this acceleration. It is not light, it is not ordinary matter, and it does not interact with matter in any way we can directly detect. Its presence is inferred entirely from its effect on the universe's large-scale structure and dynamics. Einstein's general theory of relativity predicted that mass and energy can curve spacetime, and that the curvature of spacetime determines how objects move. Within this framework, an energy density inherent to space itself, known as the cosmological constant, can produce a repulsive gravitational effect, causing expansion to accelerate. Einstein originally introduced the cosmological constant to make his equations describe a static universe, later calling it his greatest blunder when Edwin Hubble's observations showed the universe was expanding. Yet with the discovery of acceleration, the cosmological constant returned as a leading explanation for dark energy. The 1998 supernova studies involved painstaking data collection. Type Ia supernovae occur when a white dwarf star in a binary system accretes enough matter from its companion to reach a critical mass, triggering a runaway nuclear reaction that obliterates the star. Because the amount of mass needed to ignite this explosion is consistent, the peak brightness of the resulting supernova is nearly the same for all such events. This makes them standard candles, objects of known luminosity that allow astronomers to calculate their distance based on how dim they appear. By comparing those distances with the redshift of the supernova's host galaxy, the stretching of light waves due to the expansion of space, the teams could determine how the expansion rate had changed over time. They expected to see a slowing expansion, but instead, the data showed that distant supernovae were dimmer than predicted. This meant they were farther away than expected, indicating that expansion had sped up. This conclusion was not reached lightly. Both teams cross-checked their data, accounted for potential sources of error, and compared results from different telescopes, including ground-based observatories and the Hubble Space Telescope. The acceleration result was independently confirmed by other research groups in the following years, cementing dark energy as a real and dominant component of the universe. Subsequent measurements of the cosmic microwave background radiation from satellites like NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck mission further supported this conclusion, revealing that the universe is spatially flat and that the total energy density is very close to the critical value needed for flatness. Since ordinary and dark matter together make up only about 30% of that density, the rest must come from something else, dark energy. The simplest explanation for dark energy is the cosmological constant, which can be thought of as vacuum energy. Quantum field theory suggests that even empty space is not truly empty, but filled with virtual particles that flicker in and out of existence. These fluctuations should contribute to the energy density of the vacuum, creating a repulsive gravitational effect. The problem is that naive calculations of this vacuum energy using quantum theory give results that are vastly larger than what is observed, off by a factor of 10 to the power of 120 the largest known discrepancy between theory and observation in physics. This enormous mismatch remains one of the deepest unsolved problems in science. Some physicists propose that dark energy is not constant but varies over time. In quintessence models, dark energy is represented by a dynamic scalar field that changes as the universe evolves. The equation of state parameter W, which is the ratio of the pressure of dark energy to its energy density, is exactly -1 for a true cosmological constant, but can be slightly different if dark energy evolves. Measuring W with high precision and determining whether it changes with time is a major focus of current observational efforts. If W is exactly -1, the universe will expand forever at an accelerating but steady rate, leading to the Big Freeze. If W is less than -1, dark energy becomes phantom energy, and its density increases over time, eventually tearing apart all bound structures in a big rip. If W is greater than -1, dark energy's influence could diminish over time, potentially allowing gravity to slow and reverse the expansion in a big crunch. Current measurements from supernovae, galaxy clustering, and the cosmic microwave background suggest that W is very close to -1, with no strong evidence yet for variation. But the uncertainties leave room for other possibilities. To narrow down these possibilities, astronomers are mapping the universe in unprecedented detail. The European Space Agency's Euclid mission, launched to create a three-dimensional map of the dark universe, is surveying billions of galaxies over more than a third of the sky. By measuring the shapes and distribution of galaxies and the gravitational lensing of distant light by intervening mass, Euclid can track how structures have grown under the influence of dark energy. This growth history, combined with redshift data, allows scientists to reconstruct the expansion history of the universe and test models of dark energy. On the ground, the Dark Energy Spectroscopic Instrument, mounted on the Mayall 4-meter telescope in Arizona, is measuring the spectra of tens of millions of galaxies and quasars. Spectroscopy reveals redshifts with high precision, and by mapping these in 3 dimensions, DESI can measure the baryon acoustic oscillation scale across cosmic time. This standard ruler provides another way to measure distances and expansion rates, complementing the supernova approach. The Vera Rubin Observatory in Chile, with its legacy survey of space and time, will repeatedly image the entire southern sky over 10 years, detecting billions of galaxies and capturing changes in brightness and position. This time domain survey will find thousands more Type Ia supernovae, extending the supernova Hubble diagram to greater distances and improving constraints on W. NASA's upcoming Nancy Grace Roman Space Telescope will conduct wide-field infrared surveys optimized for supernova detection and weak lensing measurements, providing yet another independent probe of dark energy. Together, these missions will produce a wealth of data to test whether dark energy is constant, dynamic, or a sign of new physics in gravity. The implications of dark energy extend beyond the fate of the universe. Accelerated expansion affects how we interpret observations of distant objects, how cosmic structures formed and evolved, and even how we think about the origin of the universe. In the standard cosmological model, dark energy was negligible in the early universe, which was dominated by radiation and then matter. Only in the last few billion years has dark energy become dominant, marking a transition from decelerating to accelerating expansion. This timing raises questions about why we happen to live during the brief epoch when dark energy is just becoming important, a coincidence known as the cosmic coincidence problem. Looking ahead, if dark energy remains constant, the observable universe will continue to shrink. Galaxies beyond our local group will recede faster than light, not because they are moving through space that quickly, but because the space between us and them is expanding. Their light will be stretched to wavelengths longer than the size of the observable universe, making them disappear from view. Eventually, only the galaxies gravitationally bound to us will remain visible, and the night sky will be mostly empty. In the Big Freeze scenario, stars will burn out over trillions of years, black holes will slowly evaporate, and the universe will fade into darkness. If instead dark energy's density increases, the Big Rip would occur on a timescale that depends on the exact value of W. In some models, the disintegration of galaxies would happen billions of years before the final singularity, with planets and atoms being torn apart in the last moments. If dark energy's density decreases, the expansion could slow, potentially reversing into a big crunch that might be followed by another Big Bang, though current data does not favor this. We live at a moment when we can still see and measure the effects of dark energy across the universe. In the far future, much of this information will be lost to accelerated expansion. This makes our current efforts urgent. The work of Perlmutter, Schmidt, Riess, and the many astronomers who have followed has opened a window into the deepest workings of the cosmos, but the view will not last forever. The story of dark energy is one of humility. It reminds us that the universe is governed by forces we do not yet understand, that the majority of its contents are invisible to us, and that even the vast structures of galaxies are temporary. Yet it is also a story of human achievement. In less than a century, we have gone from thinking the universe was static to mapping its expansion and discovering that expansion is accelerating. We have built instruments that can measure the faintest flickers of light from billions of light years away, and we have developed theories that stretch from the quantum scale to the edge of the observable universe. Our fate may be sealed by dark energy, but our understanding is not. Each new measurement brings us closer to revealing what dark energy is, why it exists, and how it will shape the cosmos. We may never stop the acceleration, but we can ensure that our brief moment of cosmic visibility is used to its fullest. We can record the universe in all its richness, pass that record forward, and know that we face the vast unknown with curiosity and determination. So the next time you look up at the stars, remember that you are seeing a universe in motion, shaped by a hidden force that will one day erase much of what you see. That force is dark energy, the quiet architect of our cosmic future. Its nature will decide the ultimate fate of galaxies, stars, planets, and life itself. While we cannot escape the destiny it sets, we can choose to meet it with science, with wonder, and with an unending desire to understand. The clock of the cosmos is ticking, but for now, we are here, and the universe is ours to explore.